We are live. Hi everyone, welcome back to Codera. Today in this video we'll be discussing the problem that is Jump Game 4. This is the Leetcode daily challenge for 15th of January 2022 and it's rated as a hard problem, although I find it to be medium hard, not exactly hard. If someone is good with graphs and things like that, or maybe some general shortest path kind of things. So all those who have joined this live stream, please consider giving me a quick +1 in the chat if my voice is visible, audible to everyone, and my screen is also visible. And then within a couple of minutes I'll start with this problem. So consider giving a like to the video and please give me a +1 in the chat if everything is working fine, right? And then we'll begin with this problem. Also, this problem, that is Jump Game 4, has been previously asked in organizations like Microsoft, Facebook, and you can say Google, right? So as you can see, since this problem has been asked in organizations like Facebook, Google, Amazon, like these, so this such problems are very much important. And also this problem has some variations of it as well, like some variations. What do I mean by that? Some variations, so basically I mean that in this problem, like there can be some twists here and there, and then you might be asked to find the minimum number of jumps or something like that, right? So shall we begin with the session for today? You can, all those who have joined, so they can just give me a +1 in the chat if everyone is okay with it, right? So in this particular problem, what does the problem statement say? So the problem statement says that you have been given an array of integers ARR and you are initially positioned at the first index of the array, right? You are initially positioned at the first index of the array, and in one step, either you can, from a particular index I, you can move, in one step you can move from a particular index I to I+1 if I+1 is less than the length of the array. That is, if I+1 is valid, you can move to I-1. From I you can move to I-1 if I-1 is greater or equal to 0. That is, if I-1 is valid, right? Condition is that I and j should not be equal and array of I should be equal to array of j, right? This is also one of the conditions, right? Like, these are the steps that have been given in the problem, and in the end what you have to do is you have to return the minimum number of steps that you will have to reach the last index of the array. You have to notice one thing, that you cannot jump outside of the array at any time. You cannot jump outside of the array, right? So is the problem statement clear to everyone? If the problem statement is clear to everyone, so you can consider to give a +1 in the chat. So basically, if you are at a particular index I, right, in one step you can jump from an index I to I+1. You can jump from I to I+1 if I+1 is valid, if it is in the range from 0 till n-1. If I-1 is valid, that is, it is in the range 0 to n-1. Or you can jump to an index directly j, such that array of I is equal to array of j and I is not equal to j, right? These are the conditions that have been given in this particular problem. Now next up, what you have to, one thing that you have to see in this particular problem is that you have to find the minimum number of steps to do that, right? So let's use the whiteboard and let's try and understand this problem a little bit better. So basically the name of the problem is Jump Game 4, right? So it's the Leetcode daily challenge for today. Okay, all right. So this is the problem that we are doing now. Next up in this problem, what you can observe is that, let's suppose that you have some of the let's say you are at a particular index I, then from that particular index I you can move to an index I+1 if I+1 is valid, or you could move to an index I-1, or you could move to an index j, such that array of I is equal to array of j and j does not equal to I, like this. These are the three ways. Now for each of the ways, like for this way as well, you will be having some of the things like I-1, then you will be having I+1 for this particular I. like this, for this particular I, if suppose that this was I, right? If suppose that you pass I in this, so this will be the conditions again that you will be doing, right? Like this, each step. So if you have to consider this level, so this will be nothing but jump number 1, and this will be nothing but jump number 2, or step number 1 and step number 2, right? So I hope that this much part is clear to everyone. I'm still looking at the chats for any doubt or queries in this question, right? So this much part is clear, right? Now next up in this problem, what we have to do is we have to find the minimum, right? We have to find the minimum in this. So how do you find the minimum? Can someone let me know in the chat, how do you find the minimum number of steps? Notice one thing, that you have to find the minimum number of steps. So if suppose that I had I, from this I could move to I minus 1, I could move to I plus 1, or I could move to j, right? Let's suppose that I move to I minus 1. So from this I could move to one step back, so that means I minus 2, I minus 1 minus 1, that is I minus 2, or I could move to one step ahead, so that is again I, but I won't do I won't be doing that, right? I won't be doing that as well. And apart from this, I would be I could have moved to again I, that is one step back, right? One step back, or I could have moved to I one step ahead, that is I plus 2, or I could have moved to some variable j, right? If those were equal, right? So I hope that this much part is clear to everyone, right? If this much part clear to everybody who's in the chat? Is this much part clear? I hope that it is clear, right? So similarly you can do for this j as well, right? For this particular j as well. Now the thing is that if you will notice, can you notice that there is something connected, right? From a particular index I, if you move to something like I minus 1, or you could move to I plus 1, and from you also have I minus 2, right? So this I is connected to I minus 2, something like that. Then you have I plus 1, I plus 1 is connected to I plus 1, things like that. Like, can you see a graph? Because like you could see i's here and things like that are repeating, like there is a cycle or things like that. So what you have to do is, your I should be equal to n minus 1, and at that moment you will calculate from this, you will be starting your I from 0, and in the end I should be equal to n minus 1, and you have to calculate the minimum number of steps that you have taken. So you can see that you can get the intuition that there is some graph that is getting built on, right? That is getting built on. It might happen like any kind of graph would be there, right? Any kind of graph would be there, such that some I would be there that is equal to n minus 1, right? That I would be equal to n minus 1. So since this looks like a graph to us, like you can observe that some indexes are repeated, and we are having some paths, right? From I you can move to I minus 1 or I plus 1, then again like I minus 2, I, things are repeating. If I'll do it for this one, so this will be I plus 1 and things like that. So you have to find the shortest path, right, in this graph. So this much part is clear, that the given question can be considered as a graph. What do I mean by that? So I will say that for a particular index I, its children in its adjacency, I will have I minus 1 and I plus 1, right? So I'll say that adjacency of I dot pushback, in this adjacency I'll say that from I could either move to I minus 1, or I could move to I plus 1, like this, right? So that is why I'll say that, okay, I'll be doing this. This part must be clear, right? The intuition for this part, right? Why we are doing this? Because from a particular index the node I is connected to I minus 1 and I plus 1. That is why I'm pushing it into an adjacency list, right? That is why I'm doing this. And now, since you have to find the shortest path in this graph, because you have to find the minimum number of steps to reach I is equal to n minus 1, shortest path in this graph to reach I is equal to n minus 1, that is the last index of this particular array that has been given to you, right? According to the conditions. So I hope that this much part would be clear to everyone, right? Now next up, the situation is Next up, the situation is that how do you find, since you have to find the minimum number of steps that you would be taking to go to a particular to go to the end index, that is n minus 1, to the last index of the array. So that means that you have to find the shortest path in this particular graph that has been made, because for a node I, you can go to either the node I minus 1 or I plus 1 and things like that, and there would be a lot of cycles, and you have to consider that what will be the shortest path such that you reach from I is equal to 0 to I is equal to n minus 1 in this particular graph, right? So that is why you have to find the shortest path in the graph. And for finding the shortest path in a graph, I know for sure that for finding the shortest, just quickly comment down below, what do you use to find the shortest path in a graph? What do you use to find the shortest path, right? What do you use to find the shortest path in a graph? What do you use? So can I say that I use nothing but a BFS? Yes, I can say that. Now you'll say, why not DFS? So if you could also have said that from I we are moving to I minus 1 and I plus 1, things like that. So this looks very recursive. So I'll make a video tomorrow in which I'll be explaining like why the DFS solution would be failing, why in that case there would be some cycles or some countings which might go in the wrong way. So I'll be making a video for that as well tomorrow. Don't worry about that. But today we'll be discussing about the BFS solution only. Notice one thing: whenever you have to find the minimum number of steps, just try to think, can you make that particular problem, can you convert that particular problem into a graph? That is how I did it. Like you can see, I converted this, that I said that from the node I you could move to I minus 1 or I plus 1 and things like that. So that is how I'm making the adjacency list. And once I have made the adjacency list, so after that my graph would be ready, because adjacency list would represent my graph, right? So one more thing that I need to tell you, how to make the graph, right? How to make the graph for this particular thing. So what I would be doing is I'll be starting my I from 0, right? Making the graph for this particular case, right? For this particular problem. So I would be starting from my I from 0, I is lesser than n, and then I'll be doing an I plus plus. Once I'm done with this, so what would I do? I would have declared an adjacency list in this, and I would simply do this thing, that if my I minus 1 is greater equal to 0, so in that case it is valid, right? So I'll say adjacency of I dot push back I minus 1, right? I minus 1, because from node I can go to I minus 1, right? That means I is the parent of I minus 1, something like that. Then if adjacency, also I'll check that if my I plus 1 is lesser than n, that is the size of this array, then in that case I'll say that adjacency of I dot push back, right? Push back, or add, if you are using a list, so you can use add in Java, right? So I'll do it this I plus 1, I'll insert this thing, right? Once I'm done with this part, right? Once I'm done with this much part, so my graph would be ready, right? This is how my graph is constructed, right? If for every node I, if I minus 1 is possible, so that means that for that particular I is the parent of the node I minus 1. If I plus 1 is also applicable, that I plus 1 is lesser than n, so that means I can go to I plus 1 as well. If I can go to I plus 1, so that would simply mean that I can push back I plus 1 in my graph, right? So that means from a particular node I can go to this particular point, right? Okay. So this much part must be clear. Now moving on, one more thing that I have to tell you, that let's suppose that there are multiple instances, multiple indexes, such that let's say there is an element. Let's say there is an element. There are some elements, right? There is an element x, there is an element y, there is an element z, then there is an element x, a and b, and then x, right? So if you want to move to the occurrences of x, if you want to move through the occurrences of x, one is this one, another is this one, another is this one. So if you want to move from here to here or here, you can move anywhere in one step, right? From one particular I to one particular j, such that I is not equal to j and the elements at the index is x only, element at that particular index is x only, right? So in that case you can move. So how will you do this? So store the occurrences of same variable, same element in a map, right? In a map. What do I mean by that? So by that I mean that let's make a map in which that map would store for every particular element its number of indexes. So I'll do this like this. In this map I'll be storing a vector that will be storing all the occurrences of a particular element, right? So what I would be doing, for my I starts from 0, I is lesser than n, right, and I plus plus. After that I will say that if my array of I, no, not this thing, I'll simply push back map of, I'll say that map of array of I dot push back I, right, dot not this thing, right, dot push back I. So that I mean, what I mean by that, so I am storing all the occurrences of all the indexes at which my array of I is occurring, right? So in this way my graph is getting built. Now since I said that I'll be using a BFS approach, right, I will be using a BFS approach. So how many of you are watching? Just let me know in the chat. Okay, is this much part clear to everyone? I hope that it is clear to everyone. Now next up in this particular problem, the thing is that what you have to do is you have to simply check that what is the number in this particular problem, what is the shortest path, right? So you have to use a BFS. So can I say that I'll be using a queue? Yes, I'll be using a queue data structure in this particular program to implement the BFS. Then I'll do what? I'll declare int queue int like this, and let's say it is a queue, right? I'll be also having a visited array. So what I'll be having in this visited, let's say vector int, let's say visited, right, visited, right, visited is nothing but for n plus 1 indexes, for all the n indexes, or for all the n indexes of the particular array, and I'll initialize them to 0. All of them have been initialized to 0, or I can declare it for n only because we are taking a 0 based indexing, right? Once I'm done with that, so what I'll do what we do generally, that is while not of q dot empty. So unless and until q dot empty, so unless and until my queue is empty, I'll be traversing through it, right? What I'll be doing is I'll say that int my, let's say, current index that I am at. If my current index is what? Q dot front, right? My current index is nothing but q dot front. So if my current index is equal to n minus 1, so in that case what will I do? I'll simply return visited of the current index. In this current index visited, in this visited array, I'm not storing true and false, I'm not storing zeros and ones, I'm storing the distance, the shortest distance for it from the ith node. Okay, this is what I am doing for this particular program. So I hope that this much part is clear to all of you, right? Okay, right. So this is what I'm doing in this particular program. And next up like I'll be telling you like how we are doing this part as well. Now next up in this particular program, what I would be doing is, once I'm done with the visited part, like if I get current index is dot front is equal to q dot front, right? So what I would be doing is that I would start the traversal for a particular node, right? Also I would be returning visited of current index minus 1. I'll be telling you why we will be doing this. So what I'll be doing is I'll be starting for my int of, let's say, I is to auto I, or I can say auto I is to, something like that. Auto I is to nothing but adjacency of the current index, right? The current index. And what I would be doing is, if my if my visited of I is currently 0, so if the current index is not visited, so I'll push it into my queue, I'll push the current index into my queue, and after that I'll mark it's visited. That visited of I is nothing but visited of current index plus 1, that is visited of parent plus 1, right? Like this I would be doing. And since I'm doing a queue, that is BFS, so that is why every time the visited of I will be minimum, right? This is what I'll do. After that, one more thing that I need to do before this queue ends is that I need to store all the occurrences from the particular element. There could be two situations, right? Either I can move from I to I minus 1, I plus 1, things like that. Also I can move from a particular I to j if my I is not equal to j and array of I is equal to array of j, right? So I have to consider this case as well. And for this I have my map. So I'll say auto I is to mp map of let's say array of current index, right? Array of current index, something like this, right? So what I would be doing is, if my visited of the particular index I is equal to 0. So that means if it is not visited, so in that case what I'll say q dot push I. So I'll push this particular element, that is the instance of the current element, if there are more than the current thing, right? After that what I'll be doing is I'll say that visited of I is equal to nothing but visited of I, visited of current index, right? Current index, because current index is this, current index plus 1. So that is how I'll be incrementing this thing, right? That is how I'll be incrementing this thing. And once I'm done with that part, so what I'll do, I'll say that my map of, I'll erase this particular element from my map. So I'll say map of array of let's say current index dot erase, right? Dot erase. So I'll erase this particular let's say clear, I'll clear this particular map, right? For this particular element I'll clear this map. Once I'm done with that, so in the end I can, if I haven't returned anything, so in the end I'll return visited of the visited of current visitor of n minus 1 minus 1. So that means that my element might be, the element that I want to reach might be at the last index. So that is why I'll be returning this part. So you can obviously you might feel that this might seem a little bit tough in the implementation, but believe me, as we are doing it for the shortest part, so this will be much more simpler. You can try to dry run this particular solution on a pen and paper. Let me show you the code part for this particular problem, like how actually we'll be implementing this. So what I'll be doing in this part is, right, so let's move up, right? So I have the size, I have the visited array, I have the map in which I'll be storing all the occurrences of a particular element. After that I'll be iterating, I'll be initializing all the values that map of array of I dot push back I. So basically what I would be doing is I would be simply pushing all the values, all the indexes of a particular element at a particular position, right? Or a map will have, that's a map of 3 will have all the occurrences of the index of the element 3, that is it is having at different indexes. Then I will be building my graph, that is adjacency. If I minus 1 is valid, so adjacency of I dot push back I minus 1, adjacency of I dot push back I plus 1. Once I'm done with this, so what I'll do, I'll say q dot push 0. So I'll push the first element, I'll mark it as visited, so visited is equal to 1, although the steps are 0. So that is why if we are taking it as 1, so that is why I'm saying that for this particular thing I'll be using this thing, right? Okay. After that, while my not of q dot empty, so if my queue is not empty, in that case I if it is not empty, so whatever is the current index, I'll take this out and I'll pop it from the queue. If the current index is equal to n minus 1, so I'll say that the answer is return visited of current index minus 1, right? That is what I'll do, because I have taken for the 0th index I have taken 1, so that is why I'm saying that for the last index I have to subtract this particular 1 from it, right? Okay. After that, if it happens that it is not I have not reached the end, so if my visited of I is equal to 0, so if I haven't visited the particular element in the adjacency of the current index, so in that case I'll push it into my queue and I'll mark my visited of the current the element the child is equal to visited of parent plus 1, like this. After that I'll also traverse through this particular array to see if a particular element is not visited. If the particular instance of that particular element at the index I is current index is not visited, then I'll be marking it as visited, that is visited of the child is equal to visited of parent plus 1, although the elements are same. After that I'll say that q dot push v, right? So I'll simply push the current child, and in the end I'll clear my map. The reason for doing that is because I don't want to get into an infinite loop, right? In the end, if I haven't returned anything, so I'll return n minus 1 minus 1, because in the end I'll reach somehow the last element even if there are no connections or something like that. So I'll return the distance from the index n minus 1 to 0 if I've reached the end. And why am I doing this minus 1? Because I took visited of 0 as 1, right? So visited for the index 0 as 1, I took it like that. So that is why I'm doing this. So is this problem clear to everyone? So this problem, for this particular problem, as you can see, so since I'm using a BFS approach, so each node I am traversing once, so the time, if this much part is clear, so you can consider giving me a quick +1 in the chat. So the time complexity for this particular problem is nothing but order of n, and the space complexity for this problem is also order of n, because the reason is that I'm using a visited array and I'm also using a queue, so it is order of n plus order of n, things like that, but it will ultimately be order of n, right? Because the overall you will not consider this does not change the overall time complexity. So this is what I'm doing. So this type of problem, jump game, has been asked in companies like Google, Amazon and Facebook. So try out this problem using this approach. I know that there were people who have given the solution of this particular problem in other ways, but try to do this using graph. And I hope that I could explain why this graph was made. And since this graph was made, so that is why you have to find the shortest path in the graph, right? Shortest path in the graph. And I hope that if some people know that what is the proof, that there is a proof that why BFS helps you in finding the shortest path in a graph. So that is why we are using a BFS, and DFS won't work here, so don't worry, I'll bring a video tomorrow in which I would be explaining like why is the actual reason that BFS would fail. So this was it from my side for today, and thanks a lot everyone for watching. In case if you like the video, so you can hit the like button. Also make sure to check out the various playlists on the channel that we have. And also one more thing, like tomorrow also will be doing the Leetcode daily challenge, that is for 16th of January. So make sure that if you are unable to solve the problem, so make sure to come to see the editorial that I'll be taking live. Okay, after that one more thing, so try to be consistent in coding, and we'll be bringing the codeforces editorial that will be codeforces contest editorial that will be happening today and tomorrow. So thanks a lot everyone for watching, and I'll